What's up, you guys? Marty Schwartz here with Marty Music. I'm hanging out with Worth Dixon here of D'Addario, and we're in the R&D lab basically right now.
That's right. This lab was established about 2 years ago. We had the equipment, but we decided to consolidate it in one space so we could more easily make prototypes and do testing of our own products. We use this equipment for quality control and also sometimes to evaluate competitor products to see what we're competing against.
Oh, okay. Yeah. What's some of this gear here?
Okay, this is our scanning electron microscope.
Ooh.
So that enables us to get really high resolution, really high magnification images of our strings. You prepare a sample, it goes on a little metal fixture, and that piece goes inside the instrument. And that allows you to turn and rotate and angle and position the sample underneath the electron beam. So for example, occasionally strings break, and when a string breaks, we want to understand exactly how it broke. Was it a brittle failure, a ductile failure, etc.? So a scanning electron microscope would allow you to get this level of magnification and look at the cross-sectional surface of the string where it broke. So here you can see a hex-shaped core. So in a wound string, that's what breaks. It's when the core snaps. And what you can see is kind of this rounded shape where the material necked in and then a fracture surface right there in the center. So this is a classic image of what the surface of the cleavage plane looks like when a core breaks. This machine here is a DSC. It's a differential scanning calorimeter. Okay, and what you do is you prepare a sample. This would be for characterizing polymers. So materials we use to make monofilament strings for, say, classical guitar or ukulele, right? So you can take a small sample of your plastic or polymer, you put it in a little capsule, and then there's a furnace in this machine that heats up the sample, and then we measure the heat that's absorbed by the material. And what that gives you is this characteristic curve that shows you exactly where the material begins to transition from a solid to a liquid. So you find the melt point. So basically, that's the way you would analyze a polymer in a way that you would analyze a metal core, or wire. You might use something like a scanning or like an SEM.
What was the original stringed instrument strings made of?
Gut.
Gut, yeah.
Or silk. Mm-hmm.
Gut or silk, gotcha. Mm-hmm. Pretty fascinating.
Yeah.
Come a long way.
Exactly. Now it's all high-tech stuff.
So when you say gut though, what does that even mean?
Sheep gut.
Like literally they're cutting a thin string of it?
No, they would you kill a sheep, you clean the intestines, you stretch them and let them dry so that tubular shape necks down and forms a string.
Okay.
So that's what a classical monofilament string would be, is just a piece of sheep gut that's dried and stretched.
Wow. And the stringed instruments go back thousands and thousands of years. Thousands of years. So fascinating.
Yeah, so long before they were making steel strings, they were making strings of gut and silk.
When did a metal string first come about?
Probably the late 1800s, early 1900s.
Like a parlor style guitar or something?
Yeah, there were iron strings, so iron wire was being used. So part of the Industrial Revolution that came around.
Do you think they started doing it because it was louder or just gave different tone?
Stronger, louder, yeah, definitely. And then the other thing is that gut strings are very sensitive to changes in humidity and temperature. So it was difficult to keep them in tune.
Gotcha.
So they sound great. I mean, that's the classic sound for a classical guitar or even violin. But A, you're killing animals. B, it's an unstable material.
Right.
So there were some advantages to shifting to steel core strings. And then later on in the 50s, I think, is when nylon was introduced as a substitute for gut strings as well.
All right, we got some more high technology to
this is
to investigate.
Tensile test machine here. So it's basically this big frame that stretches things. Often we're testing strings, but you can test the strength of anything.
So do you test it to see how far it will go before it breaks?
How much it stretches, and then what force is actually required to break the strings. It helps us understand the strength and the quality of the wire that we're using to make the string from. As we're producing wire batch after batch, we're taking a sample of wire or a sample of strings and doing a tensile test to make sure that it's the correct strength, the correct elongation, etc. So you want to have consistency from batch to batch. The way you assure that is to measure it. So we just like string up a string here in these chucks. There we go. So I clamp that in there. I can run the test. Okay, you'll notice this is starting to move up.
Yeah.
Okay, so we're stretching the string.
Yeah.
And over a certain range, the string acts exactly like a spring. You can stretch it. If you were to let it go, it would retract to its original length. So that's called the elastic portion of the stress strain curve. So we're stretching the string, and at a certain point, you're going to hear it pop.
Ooh.
So there, the cord just broke. You can't see it because it's within the wire.
Oh, yeah, there you go.
The cord broke in there, and then this is the wrap wire. This is a durability tester. So we're actually simulating the string on an instrument, then picking the string to simulate the wear and tear that happens as someone plays the instrument. So
okay, and we got some a little pick on the
Yep,
robot
we have a
over
little
there.
simulated pick here. And,
Very cool.
Basically, we built this to strum strings over and over and over again.
And we're hearing compressed air, it sounds like.
Yeah, that's the pneumatic slides here in this
Pushing that through.
little mechanism. Yep.
Hold on, it's a little out of tune, man. Okay, that's better.
You got it? Yeah. So yeah, this thing is just going to pick endlessly, right? And we'll stop after, say, 7,000 cycles, and then we'll look at the string under a microscope. So our excess coating is a thin film that's wrapped around the windings of the string, and you can see it there. It makes a little web that spans the gap between each of the windings.
And it's specifically for long-lasting, to make it last longer?
That's correct. Yeah, it's to protect the windings from skin, oil, dirt, you know, other pollutants in the atmosphere that would corrode the string.
So where is that being scanned for that picture?
Over here on the optical microscope.
Gotcha.
Yep.
So you take this off and move it over.
Yeah, look
and,
at it
and
under
check
the
it
optical
out.
microscope.
Okay.
Yep. This is the workhorse of the shop
Of
here.
the whole.
Yeah, so this is our acoustic test system. One really cool thing about this is it has this 2-ton granite block. That's basically just a huge mass to isolate vibration that may be coming to the system through the floor from the factory. We want to isolate all that vibration away from the string when we do the testing. This fixture simulates the scale length of an instrument. So right now it's at a guitar scale length. We mount the string on these two little chucks. The way we're getting a signal from this string is we have a little optical sensor down there at the end. So we're optically basically measuring the displacement of the string as it vibrates. So we're not touching the string, we don't want to damp it. And we don't want to hear what it sounds like on the instrument, we just want to understand the behavior of the string itself in isolation. So we've made this string, now we want to know what does it do when you pluck it, how does it vibrate? We pluck the string by wrapping a very small diameter wire to one end, and the wire has a very consistent break strength, so that means when he pulls it and it snaps, we always pluck it with the same amount of force. So we're trying to get the most repeatable pluck as possible by using the wire like that. So that set the string in motion. We're measuring the waveform and processing it up here. So what you're seeing up there is you see the waveform. So you can see this is where the string was plucked and then it decays over time. This is the decay rate of all the harmonics from the fundamental the whole way up to like the 30th or maybe even 50th partial. And these are different ways of looking at that information. Basically looking at the decay rate of the harmonics. That's one of the most important characteristics to understand about the string to tell you if it's a good sounding string or a bad sounding string. So again, then you get deep into the science of acoustics and analyzing.
It's always amazing to see visual representation of some other phenomenon. Like that's just like a visual symbol of something else.
Yeah,
it's wild.
It is, yeah, because it's something that you can hear, but then how do you actually measure it and visualize what you're hearing?
Like, and I'm most specifically referring to that.
Yeah, every one of those traces is one of the harmonics dying off. So some of them hang in there for a long time. Other ones, the higher frequency harmonics tend to drop off very rapidly.
Wow.
So what that means is the tone of the string is actually changing over time. When you pluck it, you hear a different frequency spectrum than you do later on. It's kind of interesting. If you listen closely and you just pick a string in isolation, if you listen closely, in the very briefest moment when you first pick it, you just hear noise. It sounds like static. You'll hear a little bit of static, and then you'll hear the fundamental dominate, and you'll hear all the harmonics over top of it. And if you keep listening, as the tone dies off over time, you'll hear those higher order harmonics die off first until you're just left with the fundamental tone. So if you let it ring long enough, you'll just hear the fundamental over time. So it's kind of cool to think about that as you listen to a string once it's been plucked. And this is exactly what that is showing.
Wow, that's cool.
Yeah.
I just want to thank D'Addario and then also Worth Dixon. Thank you so much, man, for showing us around. Really, really cool to see everything and get a behind the scenes look of what goes into your guitar strings. Do you appreciate it now? All right. Thank you. We'll see you later.